Good day. This lesson will start chapter 5, which is about double integrals. But let's take a little stock. So in chapter 1, we played with functions of more than one variable and we learned how to draw them. Then we moved on to limits and continuity. Afterwards, in chapter 3, we played with differentiation, partial derivatives, the gradient, and had all kinds of fun talking about tangent lines and tangent planes. And then we saw a very cool application of all of this work in chapter 4 when we discuss optimization theory. But now it is time to play with double and iterated integrals. And you will see in a future lesson that one application is to work out the volume of a solid. So here I have a solid that is above the cone z equals to the square root of x squared plus y squared, and below the paraboloid z equals 2 minus x squared minus y squared. So we want to be able to find a way of working out the volume of this solid. But to get going, let's look at integration over rectangles. Now, why would we do this? Now, remember in first year, when we looked at the single integral, the integral from 1 to 5 of x squared dx, it was the net area below the curve y equal to x squared from x starting from 1 and ending at 5. So what we did, we typically integrated over an interval. And so if you remember first year, we did lots of integrals over intervals. Now in 114, we started by defining this concept of integrability by using this idea of a Riemann sum. So what we did, we took an interval and we chopped it up into n equals subintervals. But now we want to do something similar. So instead of integrating over an interval, we now want to integrate over a rectangle. And just like 114, we want to apply the idea of a Riemann sum, but now we have to do this in the world of rectangles and subrectangles. So how do we do this? This is how we do this. So the plan is we start with a big rectangle. So let's say we have a big rectangle, which is a subset of R2, where the x value is from A to B and the y value is from C to D. So there's a couple of ways to denote this. You can say rectangle D is the cross product of the interval from A to B and the interval from C to D. Or if you want to, you can write this in set notation. So you can say it is all the 2D vectors xy such that x is between A and B and y is between C and D. And here I have the rectangle depicted in the xy plane. So the blue region is the rectangle D that we are talking about. Now remember in first year, what we did was we took the interval and we chopped it up into n equals subintervals. But this time around, we're going to do something similar, yet a little different. So the plan of action is as follows. So we're going to partition the rectangle into lots of subrectangles. But to start, we take the interval from A to B, and we chop it up by creating a couple of new points. So x0 is the starting point, which is A. Then we select other points, x1, x2, all the way up until xn minus 1. And then the last point, xn, which is B. So we take the interval from A to B, and this time around, we randomly chop it up into n subintervals, labeling the endpoints from smallest to biggest as x0 to xn. Then we take the interval from C to D, and now we chop it up into m subintervals, not necessarily of the same length. So the smallest value is y0, which is C. The next one is y1, which is more than y0, all the way up until ym, which is D. Now by doing this, we have now been able to chop up the big rectangle into m times n subrectangles. And we can denote each subrectangle as the following. So R footscript ij. So R footscript ij is the cross product of the interval xi minus 1 comma xi crossed with the interval y sub footscript j minus 1 yj, and where I is the index from 1 to n and j is the index from 1 to m. So we define the partition of f of rectangle D as follows. So we have took the big rectangle and we've partitioned it up into m times n subrectangles. So we denote it as P equals as a set containing the mn subrectangles. So the subrectangles will be Rij, where I is between 1 to n and j is between 1 to m. So you have n choices for I, m choices for j, and so you end up creating these mn subrectangles. Let's quickly have a picture to see what's going on here. So we took the interval from A to B, and we chop it up into n subintervals. Then we took the interval from C to D, and we chop it up into m subintervals. So you see, ultimately what you do is you take the big rectangle and you make a bunch of vertical slices and a bunch of horizontal slices. So if you look at this rectangle, this is the rectangle using the first subinterval of going in the x direction, and this is also using this first subinterval going in the y direction. So this would be rectangle labeled R11. And this, if this is the ith interval in the x direction, and this is the jth interval in the y direction, then this rectangle depicted over here would be Rij. So you see, by taking the big rectangle and chopping it up this way, you're going to get mn subrectangles. And you can see the sizes of each subrectangle is not necessarily the same. And so they're going to have different areas. All right, so just like 114, we have now the big rectangle chopped up into smaller subrectangles. Now we're going to have to define a couple of new things. So we care about the area of each subrectangle. So let's define area Rij as triangle Rij as the area of the rectangle with foot scripts Ij. So that is length times breadth, and then you guys surely agree with me, it'll be xi minus 1 times yi minus yj minus 1. So that is the area. So for the x's we use a foot script I, and for the y's we use foot script j. And now we're going to need another concept. We're going to need the concept, the diameter of a rectangle. Now, in general, the diameter is the two furthest points in that region. So the diameter of the rectangle would be the two furthest points, so it will be the points connecting two opposite points. So by the theorem of Pythagoras, the diameter of rectangle Ij would be the square root of the ith interval, that distance squared, plus the length of the jth interval squared. So that is the diameter of the Ij rectangle. And we're also going to need another concept, which is the norm of a partition. So here I have a partition, and the norm of the partition is going to be notated as the norm of P. Notice, P is not a vector. P is a partition of a big rectangle into a bunch of smaller rectangles. And we're going to define the norm as the following. So for the given partition, we have mn subrectangles. For each rectangle, we calculate the diameter by the formula above, and then we take the maximum. And the maximum of those diameters, that value will be the norm of P. Great. So we now have a couple of new concepts, and now we are going to be able to find the integral. So for each subrectangle Rij, we select a random point labeled xij star, yij star, such that that point is in the rectangle with foot script ij. So remember, in first year, we took a random point in the interval. But this time around, we subdivided the big rectangle into smaller rectangles. So now we just grab a random point in each subrectangle. So it could be different as long as we have a point in each subrectangle. And now if we have a function f from D to R, so D being the big rectangle, we define the Riemann sum, R, in brackets fp, for function f with respect to partition P as follows. So for each rectangle, remember we selected a point, so we evaluate f at that point, and we multiplied it with the area of that rectangle. And so we do this for each of the subrectangles, and we add it up. And if we do this, we get the Riemann sum for function f with respect to the partition. So it's given by this formula. The sum I going from 1 to n, the sum j going from 1 to m, and then for each subrectangle, we grab a random point, we evaluate f at that random point to be multiplied with the area of that rectangle. So again, if you look back to first year, this was very similar to the formula we did when we worked out the Riemann sum for a function of one variable on an interval. Great, so we try the same ideas, but now for a rectangle. All right, and now we're ready for definition 131. So remember, we defined integrability in first year. Now we can define integrability for function of two variables. So let f be a map from D to R, where D is the rectangle, which is the interval AB crossed with a rectangle CD. We say f is integrable. So this is the meaning for when f is integrable on rectangle D. If there is a real value I, so I could be positive, negative, or naught, such that the following is true. So this again should remind you that it looks very similar to limits we did in chapter 2. So for every epsilon bigger than naught, there is a delta bigger than naught, such that for all partitions B, using Mn rectangles, and any choice of xij, yij in rectangle with indices ij, if the norm of P is less than delta, then the Riemann sum of f over partition P minus I has an absolute value less than epsilon. So what this is essentially saying is, because for every epsilon bigger than naught, there's a delta bigger than naught. So it is saying that we can make our rectangles small enough so that the Riemann sum gets closer and closer to this value I. So this condition, that for every epsilon bigger than naught, it just says that we can make the absolute value of the Riemann sum and this magical value I as small as possible by subdividing our big rectangle into smaller rectangles so that the norm of P, which is the maximum diameter of each of all of the subrectangles, is less than delta. So sometimes you've got to have lots of subrectangles, but this is the definition for f to be integrable on rectangle D. And this magic number I will be called the double integral of f over D. And we're going to have this beautiful notation where we say I equals the double integral of function f over region D. And because this is a double integral, we're going to end it off by writing dA. So telling ourselves that this is a double integral over rectangle D. So this is the notation, and this is what it means for a function to be integrable on rectangle D. Great. Now some remarks. We get many similar results as first year. So here are some results for double integrals. So this is theorem 132 in the textbook. So say f and g are functions of two variables from set D to the real numbers, both f and g, where D is the rectangle which is the interval AB cross CD. And if f and g are integrable on rectangle D, and alpha and beta are arbitrary real numbers, then the following is true. That alpha f plus beta g is integrable. And we can say more than that, that the double integral of alpha f plus beta g over rectangle D equals the alpha times the double integral of f over region D plus beta times the double integral of g over D. So this is really good news, because what this essentially is saying, if, for example, if beta is naught, then if f is integrable, then any scalar multiple of f is integrable. Likewise, if alpha is 1 and beta is minus 1, then what this is saying is that if f and g are integrable, then the difference is an integrable function. Likewise, if alpha is 1 and beta is 1, then it is saying that the sum of integral functions is integrable. So this is a really cool result. So it's not just true for functions of one variable, but it's also true for functions of two variables. Another result, we saw something similar for functions of one variable, is the following. If f is less or equal to g for all points xy on rectangle D, then the double integral of f over d is less or equal to the double integral of g over d. So we have a similar comparison theorem as we did in first year. I'm not going to prove these two theorems in the lesson, so if you're interested in the proofs, please read pages 120 to 122. It is not very exciting, and the proofs are very similar. We just have to remember how integrability is defined for functions over a rectangle. It is a little bit tedious because you can see a partition now is not just an interval into subintervals, but it is a big rectangle into mn subrectangles for some values m and n. All right, another remark. Just like first year, not all functions are integrable. So you can find a function of one variable that's not integrable on an interval. Likewise, you can also find a function of two variables that is not integrable on a rectangle. And if you want to see such an example, please tackle exercise 5.1, number 3. All right, so what we've done so far is we've defined using Riemann sum how to find the definition of integrability of a function on a rectangle. But as you know, not all regions are rectangles. So we want to continue our discussion by looking at integration over general regions. So here I have a triangle. So D is a triangle with vertices 0, 0, 2, 0, 1, 0. So this is no longer a rectangle, and we want to be able to still define a double integral, but not over a rectangle, but over this triangle D, which I shaded in blue. So this means we either have to come up with a new definition, or we got to alter our current definition. Now, if you look at this triangle D, this is a bounded set. So because this is a bounded set, we can construct a rectangle that contains triangle D. And if we have a function and we know what the function values are on D, we can just decide that the function, if it's not points not on D, if it's outside D, to have a value of 0. So if we can define integrability on the big shape with the rectangle R, then we can use that to define integrability on the region D, which is a triangle. And this was the inspiration for definition 133. So it goes as follows. Let D be a bounded set. So it's a subset of R2 and it's bounded. So since D is bounded, it is contained in a finite rectangle R. Let's say R is defined as the interval AB cross the interval CD. So now if we have a function f from D to R, and we are going to just say that function from D to R is integrable over region D. So D is the general region. If we can do the following, we define a new function and we call this function f hat. So f hat is defined as the following. So it is f at the point if the point is in D, but if the point is outside D, we define the output to be 0. So essentially what we're doing here is we extended the function on set D to a new function f hat, which is now a function on set R. So just to make it clear, the domain of f is D, and the domain of f hat is R. And R is a rectangle that contains set D. And so if the point is in D, then the value of f hat is the same as the value of f. But if the point is not on D, then the value of f hat is 0. And now we just say the following. We say function f is integrable over general region D if and only if the new function f hat is integrable over R. So remember now f hat is a function on a rectangle R, and so now we can use our definition in chapter 5.1 and quickly see, does it work or not? So if f hat is integral over r, then little f is integral over d. And likewise, if f hat is not integral over r, then little f is not integral over d. So we've transformed the general region D into a rectangle R. By doing this, we took the function f and we turned it into function f hat. And so we can now use our work in 5.1. So if f hat is integral over R, then we are happy, because then we can say little f is integral over region D. And as before, in this case, the double integral of f over d, we're going to define it as follows. It is that magical value we get when we integrate f hat over rectangle R. So the notation is as follows. The double integral of little f over general region D, dA, equals the double integral of R of f hat dA. And so we know that this exists because if f hat is integral over region R, then it makes sense to write down the double integral of f hat over region R dA. Now, time for an important theorem. Are there lots of integrable functions? And how can we find them? Well, theorem 134 is a great result because it tells us it's easy to construct functions that are integrable over regions. So the theorem goes as follows. If D is a closed and bounded set in R2, and f is a map from D to R, and it is continuous, then f is integral over D. So let me state this again. It's a very important theorem. If D is closed and bounded in R2, so D is any closed and bounded set in R2. And if f is a map from D to R and it is continuous on set D, then f is integrable over D. So this allows us to construct infinitely many regions D, which is not necessarily rectangles, and infinitely many functions f, so that the double integral of f over region D dA exists. Here is a little example that I conjured up. So here D is defined as this region. So I'm going to make this the value 7. So D is defined as this rectangle plus this triangle. So D is clearly a closed and bounded set. And now I'm going to define f as a function of two variables as e to the power x times y to the power e. Now this function is continuous on region D. So theorem 134 applies because D is a closed and bounded set, and this function f is a map from D to R, and it is continuous on region D. So therefore, the double integral of e to the x times y to the e, that double integral over region D, dA does exist. And you can see this D is not a rectangle, it's not a triangle, but it's just an arbitrary subset in R2. But important, it is closed and bounded. Great. So this theorem is pretty useful because then we do not have to worry about is the function integrable or not. So if D is closed and bounded and f is a map from D to R and it's continuous, then we are happy f is integrable over D. You don't have to know the proof in this course. I think in WTW 220 you're going to look at a proof of this result. Great. But this is important for us because now we can find loads of regions and functions for which it is integral of those functions over that region D. Great. All right. Now, as chapter 5.1, we have very similar results for not just rectangles, but for arbitrary regions D. So this is theorem 135, which is very similar to the previous theorem, and it goes as follows. Let D be a subset of R2 be a bounded set. Assume f and g are integral functions defined on D. Then the following are true. So this is my shorthand for saying the following are true. If alpha and beta are real numbers, then alpha f plus beta g are integral over D. And we can say more than that. The double integral of alpha f plus beta g over D equals alpha times the double integral of f over d plus beta times the double integral of g over d. So we see that this result is not just true for rectangles, but it's also true for general regions. So if f is integrable, then all scalar multiples of f are integrable over a bounded set. Likewise, if alpha and beta is 1, then the sum of integrable functions is again a new integrable function. And if alpha is 1 and beta is minus 1, then if f and g are integrable, then the difference is an integrable function. And this result is very similar to the one we saw, but this time around it's not over a rectangle, but it's over a general region. If f is less or equal to g for all points x, y in general region D, then the double integral of f is less or equal to the double integral over g. So again, a nice comparison theorem. We have a new theorem because now we can talk about general regions. And the result goes as follows. If D is a union of di, I going from 1 to k, so D is a union of k other regions, and if f is integrable on each of these regions, then the di's have mutually disjoint interiors. So the simplest way to think about this is an example of mutually disjoint interiors would be when if you pick any two regions di and dj, they don't have any points in common if I is not equal to j. Then you can show that the double integral of f over d is precisely the sum of the double integrals of f over each of the regions and then just adding it up. So what this result is saying, that if your region maybe has k disjoint parts, and if f is integrable on each of the k disjoint parts, then f is integrable over the entire disconnected region. So I've conjured up a small example to illustrate part 3 of this theorem. So f is the function x plus y. So we know that this function is continuous everywhere. Now D1 is this triangular region, and it's a closed bounded set. D2 is this square region, D3 is this circular region, and D4 is this funny shaped region. Now we know that if you pick any two regions, D1, D2, D3, D4, and they're different, then they don't have any points in common. So let's say D is the union of these 4 regions. So D is a disconnected set. Now, each of these DIs are closed and bounded, and because f is continuous, by theorem 134, f is integrable on each of these small regions, D1, D2, D3, D4. And so we can apply this theorem and we can say that because f is integrable over each of the regions D1, D2, D3, D4, we can say that f is integral over region D. D being the union of these 4 disjoint sets. And more than that, not only is f integrable over region D, but we can say the value of the double integral of f over region D is the double integral of f over D1 plus the double integral of f over D2 plus the double integral of f over D3 plus the double integral of f over D4. So here I have that k is equal to 4. So my region D could be subdivided into 4 disjoint regions D1, D2, D3, D4. So I hope this examples make sense. All right, ladies and gentlemen, this is just our start of our story of double integrals. More to come in chapter 5.3. So please stay tuned for the next video. Have a lovely day.